Next act, we have Leonardo Cavenaghi from Sofia International Mathematics. We're talking about 9.5.
Yeah, but then it's showing like because
9.5 weeks to move.
I mean, exactly that. All right, so thank you very much for joining this afternoon section. So indeed, it seems that our group was discovered already. 9.5 lectures and the 9.5 weeks moving. But I can say that most likely in the end of the paper will not be entitled by that. Not because I mean the joke will be lost, but especially because it's really hard to write 9.5 lectures on something that is still ongoing, right? So it's taking us a very long time to write this. So this talk is as follows. We are doing this with Maxime and Ludwig, some lectures in atom theory, which is intended to be progressive, growing, pretty good, but also it has, I mean, like a instructional character. And I consider this very good because I was learning through the way, also in some sense. But the sense is not used to be from this sort of fields when I first had to review, and then I was kind of redragged to this. And so there are many things that I had to clarify to myself. And in the process of this, we thought, okay, maybe if you want to write something to be instructive, it's for the best to try to have the words of someone that they struggle to learn. That's my case. And also, there's going to be two talks separated. One, what kind of like repetitive of the talk of 20, but trying to put my own impression on this, and also more or less explain how it is developed during this 9.5 lectures, like the sort of reasoning that you are like building from the scratch to motivate. And the second talk is more, let's go a bit crazier and see what we can get. But to start with this first part, then we shall review. And I'm sorry, I'll have to run from some stuff that Tony already spoke, and I'm sure that many of you here know very well, but I'll try to do this more direct to questions in variational geometry, but especially G equivalent variational geometry. So we're going to extend this notion of atoms to G equivalent variational geometry. This was done in a paper that's on archive with Ludwig and Maxime, named Atoms with Symbols. And to set the ground for this first part, actually maybe for both of them, X over plus, we always mean smooth projective variety complex of dimension n. Whenever you see some capital G here, it means finite subgroup of automorphisms. And we never have an action of G that's genetically free on our variety. We say that X is a divide. That's very common if you want to remember the group to say, to consider the pair. And in sort of G equivalent variational geometry questions that we are interested in, and we're going to motivate the first part of this two talks is by the means of looking to actions that are linearized. Meaning, you look to the existence of variational morphisms between your variety X and some projective space with a linear action. Meaning you can see your projective space with projectivization of representation. Okay, so this is the sort of questions that will be interesting. And we're going to do this by the means of a guiding theory. The idea, if I'm successful in this first time, is to convince you how we can approach these questions by the means of this very example here. So you pick a multi-degree hypersurface, X, that's X1, 1, 1, 1, sitting on P1 cross P1 cross P1 cross P1, right? This is rational variety over C. It's identified with blow up of P1 cross P1 cross P1 in the curve. And you're going to only look to this hypersurface that are invariant by a Z2 action on P1 cross P1 cross P1 cross P1. That's you swap first and second and third and fourth factor of this P1 to the power part. And the claim is that this pair here, the variety with this Z2 action, is actually non-linear. Meaning you cannot find a Z2 linear action on P3. This is three-dimensional variety and a Z2 equivalent variational map between them. And the same holds actually if you take cross P1 here and extend the Z2 action to be trivial on the P1 factor. So that shall be our guiding example. We're going to try to see how we can use atom theory extended to the G equivalent settings, like some sort of minor modification of the theory, to get answer to this question. But one point in these lectures that I'm saying is to try to build like from the scratch many things. We have seen that the atoms, they appear very naturally when you do this bundles, spectral covers, but also like very much the way Dragani approached this, and I'm sure that it went very nicely in this outcome guiding. This is some sort of like more geometric because of my background, and kind of will also explain these manners in these lectures, the first part. But this will lead us only to some first notion of atoms, meaning first here you should understand as sufficient to the purpose of achieving this theorem. Okay. So schedule number one, setup and a model name. Okay. So what is the setup? I'm going to be a bit repetitive in some instances, the same that Tony said, but to us, we see, we pick our smooth projective variety X over C, look to its rational vector homology, we put it as like in V as Q vector space, and it has a Poincare pairing that you can describe by this once chosen an homogeneous base. You can like keep track of these elements by looking to the coordinates, right? And again, you are reading to the system of like Z2 grading, so you want to distinguish between even and not part of your homology, and the coordinates also inherit Z2 grading. And that's common as we're gonna like delve to define what is a model that we have seen in the talk. It really has to do with Gromov-Witten theory. So to do Gromov-Witten theory, you need to like keep track of effective curve classes, and you do this by considering this model of ring. But in the end, you're gonna get a product on your very vector space after you kind of move coefficients to this node form. Now you see you're gonna have like some formal power series on these variables. This guy here is an keep technique of curves. Then you have even variables, and as Tony said, also like a finite collapse here on the odd coordinates due to symmetry. Okay, and then again, very quickly, just to set the ground, we have like the genus zero potential, Gromov-Witten invariance, and hence you have the Gromov-Witten potential that actually is an element on this big enough ring here. It has classical and quantum part. Classical part just comes from the usual cup product on your vector space, but then the quantum part is like governed by this Gromov-Witten invariance, and you see your variable here keeping track of betas. And the main point is that the Gromov-Witten invariance, they are really good to define a new notion of a product on your models that actually you can see as a family varying on some parameter space. So you define this P to be your vector space, that's your rational homology, base homology, and deserize with this, and then to specify a new product of a family of products is sufficient to say how it works on the basis at the next step. And the point is that the big quantum product has this expression. And so because these guys here depend on some parameters, you can actually see them as like families of products. And the small quantum is just okay. So you disregard these variables. I mean, after taking the third derivatives, you just compute the parameters t to 0. So it will only depend on keeping track of the curves. So far, very classic, right? I mean, not a problem, just setting the ground. A concrete example so that you can see concrete forms. As I said, these are designed to appear in some letters, not like to grow this sort of reason. When you pick X to be P2, you choose bases, H is hyperplane class, P is point class, dual coordinates, then the Gromov-Witten potential has this expression where you can see the appearance on the dependence of the coordinates. And there's some exponential here. And this ND is the number of degree D rational curves 2 3D minus 1 genetic points. Now these coordinates, you set this gamma ajk to be the third derivatives of your potential, the quantum part of the potential, and then you can actually fully describe how is the quantum multiplication in terms of the elements in the base. Very, very fast. Right? But something already starts to upset us when you have this sort of picture, is you have like some our series here. What we know already the answer that it's very tricky to do what until you have to go to the environment setting. But think that you're trying to explain this to someone. How could you do it? Why you need non-Archimedean setting? I'm saying this because I asked this myself for a year. That was like much earlier. There was no paper, atoms paper in this. So you have to do some computations to learn. And the main thing that interests me as differential geometry is that now you have your variable, your non-called variable Q. Think of this as like some complex number, and you limit its absolute value. Then actually you can show that for the potential for P2, you can pick some open domain sitting on the homology of P2 where your potential is convergent. Oops, I'm very sorry. This I didn't give any spoilers. So where it's convergent. Now, because of this, if you think about this open domain as some parameter space, like a really parameter space where you actually can pick points, then indeed you can identify the tangent space on a point on this parameter space with your homology just by assigning naturally what would be the derivations according to elements on the base. And then the quantum product acquires the notion of multiplication on your potential product. And this is, I mean, what when Tony was saying about, okay, you have a bundles, then you have like a flat connection, and this like puts the base of your manifold inside of acquires a structure of multiplication. This is super classical for people that know about like these Frobenius manifolds. But something also that cuts our attention immediately is that, okay, so if you see this Q, D, E, D, T1 here, you see that your non-code variable, it like comes depending with like some, this guy here, T1 that corresponds to H. And the point is that by standard axioms in the Romovian theory, this divisor axiom, you can just really treat together these two coordinates. And then in this case, instead of looking to multiplication of the tangent bundle of this, you can just see as multiplication in the logarithm bundle. So this is how, like, starting with your setup, assuming some sort of convergence, it makes sense to talk about like tangent bundle, tangent spaces, and then the quantum multiplication is just multiplication on tangent. There was the word like maximal over maximal in this story. What you're gonna do that we heard on stop, and there is also the model. What you're gonna do now is just extrapolate this general guys, and then over maximal means that I'm treating the variables on this M, not making this identification, not packing together Q and the variables coming from the divisor axiom. And maximal is when I get rid of them. So that's like some word of advisor for what comes. For instance, what is the general picture? Whenever you choose a base for your homology, you also, it's very nice if we start choosing them such that the first R guys here are actually a base from the Kontsevich group of the variety. And then again, by the same trick, I just eliminate and put them together. And then in this picture, whenever you identify your elements in the bases with derivations, you can pack them together. And you see that indeed the quantum multiplication is nothing but a multiplication on the logarithm tangent bundle of this guy. Red here means reduce and non-call when I incorporate the variables coming from divisor classes with the non-call variables by the means of divisor axiom. But this is formal spec. To the point. I really want something that's very dramatic. I really want that whenever, for instance, I have a convergence, I would like to have points I want to be able to have a complete geometrical picture, like having manifolds, not only thermal stuff, not only having thermal manifolds. So that's me, the justification to move on one of them, but if I'm telling a story, that's the way that I choose to tell you, to pass to this non-Archimedean setting. So I mean, you don't have actually many cases where you can prove the removal potential actually has some positive ratios of convergence. In some cases, you do get it. Like for instance, from B2, we have that estimate, and we can do this. But we want students, not stuff depending on convergence assumptions. So to do this, we actually move to this auxiliary field, who is a series, by introducing this variable here, and some valuation that will keep track of the size of these guys. And with that, all that we're gonna do in the next slide is to define what in the case of P2, we have this M as actual manifold with points. We're gonna do this like, so you pick your formal stuff, you're gonna read it, and you want to actually to build some concrete super manifold out of this. And this is the definition of what we're gonna call a model manifold. We have heard about a model F bundle. Now I'm just saying a model manifold. Okay, so what will be a model F bundle? It's just a choice of vector bundle with space. But let's get this for later. So then we start your complex smooth projective variety. Then we're going to define the model manifold as the analytic supermanifold over this non-Archimedean field that is described by the product. Three stuff. There is this tube domain, right? How is it defined? So we're going to get some variables to it, because then these variables will belong to this multiplicative group of this non-Archimedean field, seen as an analytic variety. And you pick U to be the open cone of ample classes in your variety, and you just, if this is the evaluation of your non-Archimedean field, you just do this and then just pull back. This part is what? This is the part where you're going to keep track of the non-code variables coming on your model. Now, because you disregarded these non-code variables, you have to take care of the other even variables. So you're going to think of them as elements in your non-Archimedean field with some like a small operation. And there is the purely odd part. Just specify this by the means of this functional. Okay. This is what is a model manifold. So when you look to Katzarkov, Kontsevich, and M paper, then you're going to see a model bundle. This is just the base of the model bundle. The point here is that drawing intuition on this story for B2, all that we are saying is that now we have an actual supermanifold built out of the input that's smooth projective variety. It has actually points. It has actually a tangent bundle, tangent space, and the quantum multiplication is just multiplication on the tangent bundle. So that's it. So now F bundle so far. And the main characteristic of this is geometrically then that for any point that you pick on your parameter space, the tangent space can be canonically identified with your homology with coefficients on the non-Archimedean field. And so the quantum product will make this to have like a structure of a commutative, associative unital algebra. But more than that, it comes with a distinct vector field. The plus is going to work more as like some sort of black box. I mean, okay, so you have like your manifold. I hope I can more or less convince you why we have to define this. It's very hard to convince you why I would need an order vector field. So let's take this for granted for the moment. But geometrically, now we have the manifold, we have the product on the tangent bundle, and hence the quantum multiplication itself can be seen as a tensor field on your variety. And if you have this distinguished Euler vector field here, it makes sense to take the derivatives of tensor fields, right? And then this is what this expression here says. So the Euler vector field is some natural symmetry of your quantum multiplication. And we have like talked about the quantum homology. So what's this moment? You just restrict your variables to this guy where T equals to 0, right? And hence your Euler vector field will collapse just to multiplication by first term plus, right? So this is the story. This is a very geometric story about how you can go to define what is this a model and this sort of stuff. And this is a more or less short version of what to explain the developing of these lectures. So we are ready to move to the schedule number 2. That's coarse Hodge atoms and coarse G atoms. So let us see how we can, given this geometric setup, merge it with the Hodge theoretic information and see compatibility with Bloch formulas to settle our goal, to accomplish with our goal of solving problems in G-provided variational geometry. Okay, and we do this by this Kontsevich principle. So if you talk to Ludmil, talk a lot every day, years, he thinks about Landau-Ginzburg models. So what is Landau-Ginzburg models in this perspective of a model man? So you have the Gromov-Witten potential. I'll pick two disjoint union of varieties. Kontsevich principle, let's call this, says that the Gromov-Witten potential of the disjoint union is just the sum of the Gromov-Witten. In the same way that in Kontsevich story, okay, you have like a singularity, you want to take a product, this means to add a new variable. This is the same principle. And when you work out easily this definition to see what you get at the level of a model manifolds, then you can actually realize that the disjoint union is identified with the product. And that's very crucial to us, because then this Zivitani blow-up theorem, in this very geometric setting, it will mean identifications between our variety and smooth centers by means of disjoint unions and products. So this will justify why you get like additive invariance that are results. If you put on this language, it becomes clear. And I was speaking number one fan of Zivitani, but I think this very geometrically and helped me a lot. So, Zivitani's theorem. If you pick X tilde to be the blow-up of X along the smooth subvariety of the dimension greater than 2, how we can rephrase Zivitani theorem in this set is just by the means of finding some common open sets where on your blow-up, but also on this product here that is just identified by this Kontsevich principle with the A model coming from this short union. And the point is that it preserves the quantum Euler field that you have like it's given, and the quantum multiplication. So tensor fields you pull back, Euler vector fields you push. So that's it. It's compact. So locally blow up behaves like this disjoint union. So this is what this Kontsevich picture is saying. You're not interactive because you're adding like new variables. That's it. The same way that you do this hyperset simulants. Okay, but given this sort of information, so far you have like some geometric picture, you have a multiplication of the bundle, you have a notion of blow-up formula. It's very important that you try to keep track of which kind of information coming from knowledge from Hodge theory you get. And the point is that let's denote by this hot K here. When it was explained to us that if you pick few polarizable Euro structures that are Z2-graded, the category of this guy is actually the category of representation of a group. That's not a big group. But I'm denoting by hot here because I want to that you remember that there is central element that Otto was explained was involution. So that's what I mean by hot. And hot K because I have to extend the scalars of my group to not be over Q anymore, but to be over our non-Archimedean field. And very geometrically, it will naturally act on our A model manifold just for the sake of the manner that it has constructed. We're giving coordinates. Now you just have to see, well, so how does it translate that into model interaction? The point is that on this form, like on this torus part, it is just trivial action. It's not for variables. We have chosen these two coming from an oscillator group. And it will act like a natural gradient on the other coordinates. And it has, of course, a fixed locus inside. And this is just like by definition, the subvariety of where the action is trivial. Geometrically, you can just think of this, okay, so I have a homology. This is the locus where the coordinates correspond to this, these cycles. All right, now what happens geometrically? We have discussed that we have our A model manifold, has multiplication on the bundle, is not rotate that we're noting by what acts on it, right? So let's try to see what happens. Whenever you have a fixed point, in a variety, or differential geometry, what you do? You take derivative. That's it. To see precisely is a 2D representation. So then you pick a point here on your fixed locus, and then you can decompose it as representations for your plot game. But also, you have this distinguished order vector field that you have introduced, or in some sort of black box. Then you can build this operator, because think about it. So this multiplication here is a multiplication on the tangent space at the point B. UB is a vector. You have multiplication, so you can form this operator here. That just means to multiply on the right. Now you can look to generalize eigenspace for these guys. And the main point is just because what is algebraic nature, nature of programmable invariants, these endomorphisms here is a morphism of structures. So in particular, it means that these two decompositions, they will commute. So each of these generalized eigenspaces, they can actually be thought of Hodge models. So now, or a principle, like a principle, generalized eigenspaces, they actually gain the UP grade to be treated as representations. This is the point. This is how we make these two things compatible. Have like two decompositions of your tangent space, they are commuting. One that depends, that may vary with the point, because the eigenvalues, they may vary with the points also, and hence the generalized eigenspace. And the other that's rigid. To be more precise, what you have is that this generalized eigenspace, they will decompose also as like that. Okay, so they will decompose as some representations, but because you have a product, it's even more than that. They will decompose each generalized eigenspace actually acquires the structure of a unital commutative associative. They have unit. This is going to be important to us at some point. But as you're explaining then, as you move on this EX, in this fixed locus, you may have like different amount of eigenvalues, right? Because now your eigenvalues and hence your operators that depend on the trust point. But something that happened that's very nice is that you can find actually some open set, like analysis topology inside of the fixed locus, where the number of distinct eigenvalues is maximum. So now at this guy, you collect this representation here. I can look to this isomorphism class of this representation. And if you like, also think of this representation enhanced with the structure of algebra, and you're gonna call them this shall be to us our course algebra. So I just want to think about the representation. Just this. Why are we doing this? Because whenever you're gonna do some example, you don't actually build your own model in any case. What you do is, because in many instances, you know how to compute small quantum multiplication by this guy. That's what you do. It's sufficient to already like find the eigenvalues, find the eigenspace, and fingers crossed. So you actually don't go to all this setup to this machine. This is just for the sake of building theory and proving theorems, but in like that. In your regular day, you're not gonna pick an example and write out the manifold. You actually gonna like fingers crossed to compute this and hope everything will be okay. That's it. That's what you do. So that's why you have to present it like this. In some cases, it's not sufficient because, as we were explaining, actually, this generalized eigenspace will vary with the point. How do you know you are in a very general point? Like in a point that is sufficient, the point where you have like the maximum distinct amount of variables. I remember I did this version some time ago. And then was solved. Say, how do you know? I said, I mean, You cannot gain everything. Of course, you can lose everything. And all that you can do is to hope and have some intuition in some case. Like in the cubic for photosufficiency, for instance, for the purpose to do that. Right? I know that also it's Vladimiro Benedetto Sprinkler's good Puchomukai also sufficient to do this, right? For four. So indeed, now that you have this, like in your working day as a mathematician, you want to obtain like some obstructions to rationality, you must keep track of this physical knowledge that you do. And how do you do this? Well, I mean, these are representations that were denoted like the alpha, and you can really think of them like this. Parts of your Hodge diamond. So in this generalized eigenspace, it makes sense to compute like rho alpha that is look to this generalized eigenspace. How many Hodge classes do I have? Collect this in this invariant rho alpha. And also collect the Hodge polynomial associated to this alpha. Remembering that you have to only this sort of gradient here, because you are with Hodge, very easy to place. So this is it. So what you're gonna do in your day as mathematician to do computations in order to know that it really works. You compute the quantity multiplication, you compute the generalizing spaces, and then you put invariants on them. And here's cross. Let's see how it goes. But this is it. This is the story that we're trying to tell. So you have your variety as input. There are like some inspirations of the mobility theory. You have two different splittings. And then you have Euler vector field. Funny enough, just because you're with an invariance, like the virtual fundamental class actually lives in the shell group, so it's algebra, PV, Euler vector field quantum multiplication, there are more physical Hodge structures, so everything is compatible here. And because of this Kontsevich principle, you know that when you do blow up, you're going to be able to understand additively what comes with blow ups. So because this sort of reasoning, you can expect to get the question like answers in this is the same. Now you may wonder like, okay, but it's just classical. I know this. How I can move to the G equivariant setting? If you have your variety with a finite group function, okay. Remember the way that you just build A all the time. You're just like the coordinates of this guy. Now, because the group that acts on the variety not really acts on the topology, you can just say what is the induced action during model. And then, of course, I mean, they just because I just said, you now look at the fixed locus by the action of G cross this number T. That's it. So now the representations that you're going to have are not only the representations of number T2, but actually the representation of G cross Hot. And something that's very important, I mean, is remember that story that I told you about like hoping that you're embedded in a point. You know that you have to have unit. So whenever you have like finite group action, you're going to have like a standard action tomorrow. But you know that your group action also has to preserve unit. Because these are like the unit logics. Because of that, in many cases, you know that you are in a point general now. Because otherwise, if you move on the locus, and then you are forbidden to have more eigenvalues just because you're gonna have like some pieces that do not like it's not a representation on an output because it will like think about like the heuristic C2 actions. So it like has evolutions like plus and minus one. So they cannot like show up because there's no unit. Since that's the sort of reason. So all that I'm saying is that whenever we have group actions, the eigenvalues they come together. You expect to have lesser eigenvalues for the quantum multiplication moving on the locus of the invariant guys. That if you don't have group actions. So that's like how the theory. I mean, this is some sort of heuristic, but also precise explanation on why a variety can be rational over C, but need not to be rational, like G equivalent variation to some. That's the point. Because now we are packing together, looking for representations of G cross. And in this case, we just gain a new invariant. That's okay. So you have like a space. This corresponds to a piece in your Hodge diamond. But now you can need not only to keep track of the Hodge classes, but you can keep track of like the invariant Hodge classes. And now to solve the motivation problem that we started with, what we do is just, okay, so all that I need to know, I know that variety over C can be rational, it's rational, and species should only come like activity from Boa. You think what you do now is more or less the same story. I mean, not more or less, but the same story. You just need to know like which pieces can come from blow up along these loose invariant centers on your variety. Actually, provide with factorization theorem. That's it. So the variety that we started is three-dimensional. So we need to know whether like the atoms that we compute to them actually can come from like are all the atoms coming from blow-ups and points and curves. And that's to do this, we can actually classify all the possible G force Hodge atoms coming from points and curves. So you have a finite group action on your variety. Right? So what are orbits? Orbits are the G mods and stability. This is GH. So classes coming from points are actually like the orbits of points or fixed points. And for curves, it's just like some orbs of the curves. And the point is that you can actually verify that for an atom coming like a G, for example, coming from points like or curves, either the invariant, the number of invariant Hodge classes is 1 or 2, but you also have the Hodge polynomial. If the Hodge polynomial is constant, necessarily is 1, the number of invariant Hodge classes. We do this computation, carefully explain how you can classify this on a complete symbols. And here, I mean, we oversimplifying here G is a bigger group. You have to take care of some groups. I mean, when you restrict subgroups, as I'm sure that just going to explain us. I mean, there are many subtleties that you have to take care because, okay, you're going to restrict to subgroup actions. How is it? I mean, how it becomes. But the point is for medium groups and in these various tiny dimensions, you can actually make a list. And with that, we can simply solve the problem that we started motivating. And we do this with fingers crossed. So we start with your smooth hypersurface. It's a blow up of P1 cross P1 cross P1 limit curve. Assume that you're with this variety that are invariant under the induced Z2 action from the ambient. And then you do computation, small quantum multiplication. Multiplication by first order class. That's what we do. Then you can check that there are actually 3 eigenvalues. They even have numbers. 16 or 0. So the eigenspace corresponding to 16 is one dimensional. It has one Hodge class and one invariant Hodge class and constant Hodge polynomial. Yeah, sure.
So when you say this group just swap factors, you mean it's really swapping, no twisting?
No,
Just the few.
just the
So theoretically, if you have another swap equation twist, everything will change.
Yes, exactly. Yeah, it's not the universal truth. It's case by case. Yeah. Because the invariant, I mean, for instance, this happened yesterday, as we saw. Indeed, so if you do some computation with your small quantum multiplication, you can get some eigenvalues. But you know that you have to move on along invariant part. But if you don't are actually very careful to make sure that you are like computing the eigenvalues for the parameters that are invariant, you can get more eigenvalues. Then you can like make mistakes. That can happen. So it's short in this case because I'll tell a story very quickly. That's the point. So when we were writing this chapter in the lectures, I wanted to say that this is some sort of extension of Griffiths, Clemens and Griffiths' story, like the spiritual succession. Then Maxine agreed, but Ludmil terribly disagreed and said, "Let me write this part." Never, because he doesn't agree with this. But the point is that it's okay. So what do you mean by this, right? Because so the point is that why not? Right? Why this terminology? And it's very counterintuitive also the terminology. I can tell the answer from what he quoted in 2003. He said, because they wanted to get splitting. I mean, this is literally not the Greek name of atom, right? They don't want to keep like a splitting. And this is what we're talking about. They say that's the point. I don't understand. I mean, it's even more confusing now that you say it. But so the point is that this is different from Griffiths and Harris because sorry, not Harris, but Clemens and Greeks, because there you have like polarization, then you have like irreducible stuff. These no, I mean they want to get decomposed. That's the point. And you have to be very careful with that. That's how we genetically can make mistakes. And so we have to make sure that you're varying and then making sure that you're having the correct numbers of eigenvalues and this sort of stuff. So they're soft. Study was explained. So in this case, then we have then the other eigenvalue 4. That's like a 4 Hodge classes, but only 2 invariant Hodge classes. And the polynomial is also constant. And then you have the eigenvalue 0 that has 5 Hodge classes, 3 invariant Hodge classes, and has this Hodge polynomial. Non-constant. But you know that this guy here is blow up of P1 plus P1 plus P1 elliptic curve. So its homology has to have a factor that resembles a elliptic curve. This is what is studying here. Now, if you compute the number of invariant Hodge classes, you have like 6, while you have 10 Hodge classes in general. Now, what you do? I claim that the main obstruction comes from this big eigenspace here. How do you do this? If the G action was linearizable, atoms must be constructible from atoms of the 3 and the varieties of dimension, 2-dimensional, because this is the dimension. Now, by using our lemma, you can check that, okay, points can contribute for Z2 actions with the following numerology. 1 Hodge class and 1 invariant Hodge class, 2 Hodge classes and 1 invariant Hodge class, and the elliptic curve can also contribute with 2 Hodge classes and 2 invariant Hodge classes. In the atom at 0 here, we have this parameter 5, 3. But you know that because this is blow up of P1 plus P1 plus P1 curve, the atom at 0 has to have the contribution from this elliptic curve. So then in this atom now is just take out the contribution from the curve. You get 3 and 1. Now, I mean, you definitely get a contradiction because this 3, 1 cannot be written as contributions coming from points. That's the point. You cannot, so that's like how you get sort of contradiction by numerology. I'm saying that these atoms, they are additive invariants, right? So then you know how these invariants they interact, and then you do your computation, find something that looks like an obstruction. Now I have to prove it actually an obstruction. And in this case, because the contribution for points, I mean, in rational curves, there's like some big line here, but rational curves also contribute as the same as with points. And then you see, okay, so the contribution for the curve is given already. Now, what is that? It's 3, 1, but they cannot have contributions. This is how we do it. And with this, I finish my first part. Thank you so much.